Get that going. Okay, so let me bring up the quiz, and we can talk through it, and then we'll get into pointer stuff. Just typing in pointers. Okay. All right, so first question. Which of the following are benefits of using an STL array, standard array, as opposed to normal arrays? So we've got the ability to always grab the size of the array, the ability to easily sort, both A and B, and none, right? So you can always get the size. We've got the size method built into standard array, right? So A is definitely something that we get. B is also definitely something that we get, because if we include the algorithm library as well, we can use the sort function that it defines, and we get an easy, nice way to quickly sort, right? So since we've got A and B, obviously C is the right answer, right? So that's pretty standard. Okay, so if you need a list, number two, if you need a list-like object that can grow in size during your program, what do you want? So the answer is A, vector, right? So the only other, array is definitely a contender since I'm asking for a list-like object. And I was careful. So lists can be a lot of things, right? If I say a list, you think of a number of objects in some order, maybe, or a collection of objects, right? Arrays are definitely something that do that. We touched a little bit on linked lists a couple classes ago. I forget which one it was. So that's another thing. That's why that's why I use the term list-like, because there's actually, it's not just array or vector. There's a whole range of things that kind of are good or list-like objects, right? So anyway, so an array is definitely a list-like object, but even a nicer STL array is still fixed size. So that invalidates that. You could kind of make an argument that a string is list-like. A normal string, in standard vanilla C, we don't even have strings. We have character arrays, and that's it, right? So it is a list of a kind, right? But only character type. So I think that that's really stretching things a bit to call a string a list-like object. Because if I was saying I needed a string, I'd probably say a string, right? So anyway, so that invalidates that. Algorithm isn't a data structure at all. It's tools to work on other data structures. That's where we get things like sorting and various other things, but it's not in and of itself a data structure, right? So vector is what we want, and that's one of the cool things about vectors is that they do grow and shrink. How they do that is, it's still, it's not magic, right? So if you wanted to implement a vector, what you would end up doing is you would still have a fixed size array. There's one way you could do it, at least, right? So what you would do is you have to, because when you declare memory in C++, which we're going to talk about a little bit more today, you always carve out a specific block of memory. There's no way around that. That's just the physics of computers, right? So even vectors that we can treat as being not fixed size are implemented using fixed size components, right? So what you can do is one way of going about it is you can just make an array. Like let's say we just make an array and we make it 10 or something, right? 10 elements long. Then when we go to insert the 11th element, what we do is we actually make a new array that's double the length. And we copy all the elements over. So that's one way to do it. It's a pretty typical way to do it, is you kind of store one fixed length thing and the current size and current number of things in it. And when you're about to exceed your size, you just remake a bigger box, essentially. And then you copy everything over. So vectors aren't magic, but you don't want to reinvent that, right? You can trust STL to be a nice, clean implementation that you can absolutely trust, right? So trust the STL is a good thing. Anyway, okay, so what does the template and the standard template library stand for, or refer to? So the answer is definitely that the ability for a given piece of code to be run with multiple types of input. And as I was writing up the explanation, I realized that that description is a little bit bad, so I apologize for that. But what it's getting at is we can have different types, and by type I mean the strict definition of type, meaning like int is a type, bool is a type, ogre is a type, right? Because we make our own types when we get to classes. So all of those things, right? So you can make one function or one class that can receive multiple types. So that's the key thing about templating, right? The classes should only be used in certain situations. Not really. STL is generally a good thing. It's they're general purpose tools that are hammered on really hard to be robust and well implemented and reliable and efficient. So mathematical filtering of input data, no, the STL does a lot of different things. You can find some mathematical stuff in there, in some cases, but it's not general purpose. Range checking on things like arrays, yeah, not really. It's because, again, this is more general, right? STL does a lot of stuff, right? So, yeah, D. Okay, so last, not least, look at the following code. Add a single line to sort my array in ascending order. So the single line was key. And, this is something you kind of have to memorize. And I agree, if you say that this seems like a lot of, or sort of an odd way to put it, I'd agree, right? If you're used to other languages, you'd probably expect just myArray.sort, right? That's a really common thing in a lot of different contexts. Not so here. And so we have this kind of weird syntax where we have sort, and then we pass in myArray.begin, which is a function that we call, because we've got parentheses, right? And then myArray.end, which is also a function. Kind of odd, right? But what that's getting at, once again, is this concept of iterators, right? So iterators is another thing that the STL uses to make things interoperable, right? So an iterator lets you refer to a specific place in a list-like object, right? So in a vector, in an array, in various other things, they're kind of like a list, right? We can talk about a place in that list, right? We could define our own, ogre cave, right? That has a lot of ogres in it, and we might want to talk about a specific, inf ogre in that list of ogres, maybe, right? So what we're doing is the begin is something that just returns the start of a list-like object, and end returns the end of a list-like object, and then that lets the sort function take this iterator and know where to start and where to end and kind of process its way through. So it's roundabout, right? Definitely a little bit weird, but the reason it's that way gives us something really nice, in that it gives us the ability to take that same sort function and use it on a wide range of different types of input. So we can use it on an array, we can use it on a vector, we can use it on our own custom classes, as long as our custom class also defines a begin and an end. That provide handles to something that's the start and something that's the end.
But we never call begin and end, right? That's like a built-in thing.
Oh,
that understands.
We do call it.
Call those?
Mm-hmm.
Like,
So, I see what you mean. So, no, you absolutely can. So, yeah, so there are times when you'll want to get you'll want to grab the beginning. And actually, I'm so glad you asked that, because we're going to see that later today. So later, this is something I wanted to get into last class, and we didn't quite have time for it. But later today, what we're going to do is we're going to make a really, really simple text adventure. So what it's going to let us do is there's going to be a number of rooms, and each room will have some number of objects in it. And what we'll do is we'll be able to move from room to room. We'll be able to pick up objects from the room into player inventory, and drop objects from player inventory to the room we're in. So one of the things we're going to need to do in that case is we're going to need to search to see if I'm trying to drop, like if I say drop rubber ducky, that should only work if rubber ducky is in my inventory, right? So what I need to do is I need to look through, we're going to use a vector of strings, and we're going to need to see, like, is there something rubber ducky, and is that something that exists, right? And one of the things we can do, I'll come back to this, obviously we're going to see it in practice a little later today, but if you use the find function, right, to look for a specific element in a vector, is another thing we get from algorithm. If it's not there, what we'll end up with is end. So the value that we get will either be, it is an iterator, but it will either be a location in the thing, or if it's not found, it'll be equal to n. So good question. Yeah, there are absolutely circumstances where you'll want to call begin and end directly. Good question. Any other questions? Cool. All right, so that's that quiz. And like I said, no quiz today, so we'll skip one. Okay, so today, I should give out the handouts. So today we get to talk about pointers. And it's kind of, I wouldn't be doing my job teaching you guys C++ if I didn't scare you a little bit about pointers. But it's hopefully it's more like the scare you get in like a Halloween scare, not an actual, terrifying situation scare. Because what we're going to do is hopefully we're going to try to make sure we kind of peel back the rubber mask and we'll see it's not that bad. Hey, Shane. Don't forget I got your quiz for you. There you go. Okay, so I've tried to kind of edge towards pointers a bit in classes that we've talked about so far. And, I maintain that there's two reasons people find pointers confusing. One is that it forces you to think about memory in a deep way. That's a really good thing ultimately, though. So that's one of the big benefits you get by studying C++, I would argue, is to be successful with C++, you have to think about memory in a very sort of very deep way, right? You kind of have to be closer to the bones of your machine. And, that can absolutely be frustrating, but it also makes you a better engineer. So I don't know how much C++ you guys are going to write in your professional lives. You can absolutely have a long career in game engineering and write little to no C++, especially these days. That's totally possible. But I do know for a fact that getting comfortable with these kind of concepts will absolutely make you a better engineer. So, that's one thing that makes pointers a little tricky is the key concepts, you kind of have to think about memory a lot, right? But it's a good thing. The other thing that makes pointers tricky is honestly the syntax is just kind of bad, I would say. So what we're going to see, and bear with me and be sure to ask a lot of questions, is we're going to see, as we work through what pointers are and how they work, we're basically going to see two characters used, ampersand and asterisk. And we're going to see them used in multiple ways. When we already have ampersand being used in multiple ways in a different context, right? So, if it was up to me, ampersand wouldn't be used at all. And the two uses that we're going to see ampersand put to would be two separate symbols. And the two uses that we're going to see asterisk put to would also be two separate symbols. I think if that was the case, this is just me, I'm just opinion, right? I think a lot of people would find pointers a lot easier to deal with. But anyway, so key thing, right? And this is why I made sure I made it nice and big on the handout and in the class materials is the key, underlying principle is that a pointer is just an address. That's all it is. It's just, it's nothing all that scary. So, if we could crack open our computer memory, right, what we would see, conceptually, at least, we can think of it as a long row of boxes. So just one long strip. So you can basically think of computer memory, and it's not even that different than this, actually, physically, as just a long row of boxes. Or each box is a byte. So, what we've done so far in class is all the time, right? Is we're constantly making variables, right? So when we say, "Hey, computer, I want an int," right? So exactly how big that is depends on our system, right? So modern days that probably means 4 bytes. So what happens is the system decides it finds some location that has 4 bytes free, right? So if we say my int, so the equivalent of saying when we say something like my num, int my num, right? Now I haven't set this value to anything yet, right? I've declared it, but I haven't initialized it yet. But just declaring this is causing something to happen, right? So it's saying that somewhere, we know that it's a normal int. It's not a long. It's not well, unsigned wouldn't matter, but it's not a long, it's not a short, right? It's vanilla int, so it's 4 bytes, and I need to find some place that has 4 bytes free. That's totally fine, right? So system does that, and let's say it's these 4 bytes, right? So, and we can think of these boxes as just being strictly numbered, right? So the specifics of where in memory we are at the moment don't really matter, but the numbers are there and they're contiguous, right? So if this is something like, I'm going to abbreviate it just because I don't want to write out the full long hexadecimal thing, but if we've got something like this box might be OX0192 or something, right? Meaning that this is OX0193, and that goes on and on and on, right? So when we say int mynum, we're saying find a place, but the key thing is we're not saying where that place is, right? That's not our decision to make. And this is why pointers become important. So what a pointer is getting this actual address. So it's a little bit like, think like you go to a sandwich shop and you say, I want, turkey avocado with provolone. It's my favorite sandwich. So you ask for that, right? And you get a number. Now, what number that is, does it matter? Not really. But when you go to claim your sandwich, you better know which number you're grabbing, right? Because there's a whole bunch of sandwiches that are just these white, cylinders, right? And you might end up with roast beef, which would be kind of sad if you're looking for turkey provolone. That would make me sad. You guys might be happy. So, and if you go back to that same sandwich shop the next day, right, you'll get a number again. If you say, give me a sandwich, give me a turkey provolone sandwich, you'll get another number, but it's highly unlikely it's going to be the same number, right? It might be. They have some sort of rotating thing of 100 numbers, let's say, right? And that's kind of what computer memory is. It's like, it's got a set range of numbers, right? In any given day at that sandwich shop, or any given 20-minute period, it's unlikely that they're going to go through their entire range of numbers. But it's also not the case that those numbers increment forever. There's like some finite number, right? You go back in a year, they're still in the range of 0 to 100, probably, right? So I don't know how. Hopefully that helps a little bit. But what I'm trying to get at is that we don't specify what the number is or where to put stuff. We ask the system to do that for us, which is important because the system can find a space that's big enough, right? So, and this is this is a reason why C++ is strongly typed. So if we didn't say what type of variable we were trying to make, then there'd be some problems, right? Because by saying int mynum, then we know that we need 4 bytes, which is fine. We might have a data structure that is way bigger than that, right? And that's okay too, as long as that's declared, right? So anyway, so that's really all a pointer is. Now, why do we care, right? So we've got int mynum, right? So if I fill it up with, if I say it's 4, let's say, we'd have zeros, just 0, 0, 0, and then in here we'd have so we'd have this byte, which is 4, right? So in the least significant byte. So so then we filled it up. So now we've said mynum equals 4, right? Okay. So now we've got, for most of what we've done in class, we've only ever worried about the 4, right? But there are a lot of situations where you want to worry about the address too. Now, why is that, right? So the biggest upshot, really, is that it allows you to do something called pass by reference. So we've done, so we've looked at some functions so far, right? And generally what we've done is something called pass by value, meaning that we do something like this. We say, int, or let's say void maybe, just to keep it simple, do stuff. And then we'll pass in int num, right? And then we do something with that, right? And then we call that with do stuff 23. And mainly that just works, right? So that's all fine, that's well and good. And for simple data, like just ints, Totally fine. Great. But what's actually happening there, we'll come back to this in a little bit once you start digging in the code, is we pass in this value, right? And when it hits the function, it actually gets copied. So that's totally fine if all we're doing is an int, right? And if what we want to have happen with this 23 is we just wanted to, like maybe we just want to print one of two messages if the number is bigger or less than 20, right? So if that's the case, that's all fine, right? But what happens, and I know you guys, this has come up for some of you guys. I know, Carly, you were wondering about this for your weather, right? So if you want something to get passed in and then it be altered, there's no way to do that with this. The only way to do that is with global variables, which we've been using a lot this semester, right? So far, just because I had to get you guys started. But global variables are to be avoided whenever possible. At the stage you guys are at, starting out, just kind of assume that a global variable is always wrong. That's not strictly true, but that's closer to the truth than thinking it's totally fine to have global variables everywhere. So anyway, so that's one reason, right? So if we want to actually, alter something inside this function, then that's one reason we might want to pass by reference, meaning that we don't pass in the actual value. What we do is we pass in the address where the value lives. So it's kind of like, if you wanted your friend to pick up your sandwich for you, you'd give them the ticket, right? And you wouldn't say to them, you wouldn't say, go order a turkey provolone for me, because you already did that. You called it in, let's say, right? What you would say is pick up sandwich number 23, right? And they, if they wanted to be a nice guy about it, they might do that for you. So, but they wouldn't know anything about, it's completely separate from the contents of the sandwich. Right? So that's one reason. Another reason you might want to pass by reference, and this gets really important, especially with games, right? So when you're doing game programming, so far I know we've stuck to, just text, and I hope you guys have been enjoying it, but I know it's not the most exciting, just a good way to get started, right? But eventually you guys are going to be working with graphics and sound and 3D models and textures, and all of those things are nothing you want to ever pass by value. Because if you're talking about something like a texture resource, you're talking about, it might get loaded in as a PNG. It might exist on the hard drive in some nice compressed format, right? But once it's actually getting used by the computer, it has to be unpacked. And it wouldn't take much if you were passing stuff like texture data around by value. That'd be bad. You'd have this big chunk of memory, right? And you'd be essentially duplicating it all the time. So what you want to do is you want to, give that big chunk of memory someplace to live, and then just know where it happens to be. Right? So once you have something with kind of some heft to it, like a texture or even just a complex data structure. For I'll go back to my ogre example, right? You'd probably want to pass around just here's where that thing lives in memory, I should say, just because we're talking about ogres, right? So I'm not talking about the game equivalent. I'm talking about just where it is in memory, right? So the first byte where it starts. Okay. Usually, yeah. So basically, it's like, you kind of have to do it, honestly. It's like you don't worry about it so much if you're just passing ints or whatever, right? That's fine. But there's two main reasons. If you want to work with something that's not a simple data type, like an int or a character or something, right? That's one reason. Or if you're dealing with something, and generally, actually, these are both the case now. If you're dealing with something that's large, right? Now, a large thing is also unlikely to be a standard data type. But you could actually, okay, so let's say you were doing something like bioinformatics, which it might involve a very, very, very large string. Because you might have something that's just text, but it happens to be the text for the entire genome sequence for a fruit fly or something, right? Big chunk of data, right? You do not want to pass that around by value. You want to just store that somewhere and give a reference to it, right? So, yeah. So in practice, a lot of what you do is going to be passing by reference. Also, if you work with APIs, right? So, at some point, like if you guys want to do full-on GUI programming, you'll see a lot of this, right? So In the Windows API, there's this concept, and you'll see it in other places too, of a handle to something, right? So you make a window, right? And you have your main window, and then you want to do things to it, right? So generally, what you do is you pass a reference to that thing around to various API calls. So you might need to set the brush. There's this concept of brushes. I haven't done Windows-specific programming in a while, but so there used to be this concept of like brushes that you would set to like red, and then you could draw with it, and that's one way to get really simple 2D graphics to happen in a Windows-specific sort of way, right? So you might have to set the brush to some color, some new color, right? So anyway, and that's you could, right? If you were doing it all yourself, you could just give yourself global variables, but you're not going to do it all yourself. You don't want to do that. You don't want to write your entire, like interfacing with the OS. You don't want to. I mean, maybe you do, but I want to recommend it because you guys, I assume, all want to make a game, right? And the way to make a game is to not reinvent everything, right? So yes, you're going to have to pass stuff to APIs, and like the Windows API, expects to get a handle to the window you made for various things. So, okay. So let's talk about actually using pointers. So I'm going to make a new project here. Oh, let me go ahead and get my screen shared. I always have to. Team meeting? Team viewer, yeah. Okay. Meeting. Okay, let's see what we got. We got 83, M83. 017. 961. Okay, so I'm just going to make a new project. Nothing new here. Not Visual C. Sharp, rather. Empty project. And I'll make a new source file. C++. And I'll start out with standard stuff. So I'll include IOStream. And this is tiny text. So let's fix that too. Options. Fonts and colors.
You can actually hit Control and hold the mouse.
Oh. Yeah. Control in. Sure, it's Control in. It's just give me a new file dialog.
Control your mouse.
Control and okay. Oh, okay. Yeah. Thanks, guys. Yeah. Awesome. Cool. There we go. All right. So no. Although somehow the settings got reset, so I'm going to make sure we get line numbers because it just offends my sensibilities to have a text editor without line numbers. Should offend your sensibilities too. It's ridiculous. So text editor general, all languages, yeah. Thanks, Ronaldo. There we go. All right, there we go. All right, so standard stuff. I'm just gonna using namespace standard and int main return 0. Okay. So the first thing to talk about with in relation to pointers is so a pointer is just an address, right? It's just the address of a thing. So that kind of brings up the question: how do we get the address? So that's the first thing we're going to do. So I'm going to start off with just int mynum, and I'll set it equal to 23. I like that. And I'll just for the sake of keeping stuff around, and I'll say int input. Okay, so now obviously we can say cout mynum new line, right? So that's going to print out 23, nothing special here, right? So let's say I want the address of that though. So what I can do, and this is where it starts to get confusing, a little bit, but I would say mainly because of the syntax. So apologies for that. Is I'm going to use the address of operator. So I'm just going to type in, then we'll talk about it. So I'll cout ampersand my num. Okay, so the ampersand used like this has a totally different meaning than stuff we've seen before, right? So we've seen ampersand before to mean both logical and bitwise and, which I think is a great use for it because ampersand kind of means and, right? In normal written language. So when you see it like this, though, in an expression, because it means something else in a declaration, which we'll get to later. So the important thing here is, so declaration meaning, something like this, right? Int my num, that's a declaration, right? If we just say my num plus 2, that's just an expression, right? An expression's like a little bit, it's sort of like a little snippet that doesn't create a new variable, it just operates on variables that exist. So when we see ampersand like this in an expression right next to a variable name, what this means is the address of. You can think of it just like that. Just think address of whatever it is, right? So let me run this, and let's see what we get. So we get 23, and then we get 0018FCC8. So I know it's a little hard to read. The key thing is we've got the actual value, right? And here we've got the address. Now, do we care about the address? Well, we don't care about the specific value of the address, right? It doesn't really matter to us that that's in that specific location, but there's a lot of reasons why we might want to deal with where it is, right? Do something with that. So that's one big component of pointers. Not too bad, right? Just put the ampersand right next to the variable, you get the address. Not a big deal. But that's usually not going to be that useful to you in and of itself, right? So this is not something we would normally want to do. The only thing I can think of is you might want to see, this could be something you use to check to see if something is exactly the same thing, right? So if something it happens to be the same value, right, we might have two variables, both with the value 23. But if the address is the same, that means it's the same thing, right? So that can be one way to check for sort of strict equality. Doesn't really matter for ints, but you could say, like, let's say we've got two ogres, right? We might check to see, well, are they named the same and are they the same height? Does that necessarily mean they're the same ogre? No, right? So we might get some weird behavior if we say, oh, well, they're both named Fred and they're both 6'2". So I'm going to assume that that's exactly the same ogre. But it's actually two different Freds that just happen to be the same height, right? So, but if I knew that the address where they were located was the same, then I could be confident knowing that that really is the same ogre. Right? So that's one thing you might do, but that's kind of special case, right? So anyway, so good so far? Not that hard. Yeah.
If I go to the equal 23 next to my num, that means I can grab all numbers for my num.
Well, so if we get rid of the equals 23, it's a good question, right? So what changes if we get rid of this, right? What we've done is when we first started talking about variables, we talked about how there's a difference between declaration and initialization, right? So declaring carves out a piece of memory for you, for that variable. Initializing, sets the contents of that memory, right? So what I've done now is before, when I had int my num equals 23, I was doing both, which is a pretty standard thing to do, especially with integers, right? You declare it and initialize it all in one fell swoop. So now we've got a blank integer, right? But we've still carved out a piece of memory for it. So this may just end up being 0 if it's nice to us, but or it might be. Let's just see. Yeah, it's not going to let us do it. All right, so that's actually good. So sometimes compilers are more or less strict, right? So it actually didn't let us run that because we're couting my num without ever having set it to a value. But So that kind of makes sense, right? But if I comment out the line that prints out the value, we can still print out the address. Even though we haven't given it a value yet, but by virtue of just declaring int mynum, we've carved out the chunk of memory, meaning that there's a valid memory address for that thing. So try that. We get, some memory address.
So the address will be changed.
Oh yeah, so don't assume that addresses will ever be the same. You should sort of just assume that they're random. There is one difference, one sort of side note to that when we'll talk about pointer math in a little bit, where there are some things you can do with pointers to change their value directly that can be useful. We'll get to that in a few minutes. But in general, you kind of want to take it as random. Just like you go to the sandwich shop, it doesn't matter what ticket number you get, as long as you've got the ticket number that corresponds to your sandwich. Right? Yeah, Anastasia.
So, we just ran that before, and then did the address of the place that it was originally, does that get cleared?
Good question. Right. So that
We kept running this, but it keeps storing new.
great question. So that's actually a pretty deep question, right? So what it gets at is memory management. So far, it would get cleared. It would be marked as fine for reuse. So remember, nothing ever gets deleted, right? What happens is it gets marked OK for reuse, right? And that would happen because we've got just sort of a standard. So this gets back to scoping. So we've talked a little bit about variable scope, right? So when we declare this variable, it's in this block. Now this block happens to correspond to int main, right? But we don't ever have to really worry about that. The key thing is it's in a block of code, right? So any variable that gets declared in a given block of code, just we declare it locally to this block. Once we hit the end of that block, it's freed up. Unless we do other things that we'll talk about later, right? So there is, and I think this is on the docket for next week. You can do explicit memory management. So you can say new integer. Now that's a little different, because what that does is that carves out a chunk of memory, and it doesn't get freed up at the end of that block, which is sometimes what you'll want, but that means you have to be careful to free it up later. So, because as your program runs, if you're declaring a lot of memory and not freeing it, then you'll crash your program. Right? It's not going to hurt your computer, but that's how games fall over. Right? I think everybody has had the experience of having a game get a little weirdly sluggish or a little bit unstable and then crash. Right? And a big cause of that is some sort of memory error, where something is what's called leaking memory. It's declaring memory and not cleaning it up. So everybody does it. It's it's a common type of error, and it's very easy. So you have to be really vigilant about it once you start doing dynamic memory, which we're not doing yet. So we don't have to worry about it too much yet. But really good question. Good so far? Okay, I know that's a really simple thing, right? But I want to make sure everybody's good each component along the way. Okay, so that's getting an address, right? So the next thing I want to talk about is you can also have a variable that is of type pointer, right? So let's say I know I want to store the address. I want to pass it around. I want to do something useful with it in the context of my program. And so what I want to do is I want to declare an int, not an int, but an int pointer. So let's look at what that looks like. So I'm going to go back to giving this a value. And I'm going to say int asterisk my PTR pointer. And so in and of itself, that's not that useful, right? So what I've done so far is this asterisk directly next to the name is saying this isn't just an integer. And I mean, technically it is an integer, because technically all pointers are integers. Technically, right? Because it makes sense, right? Because when we're talking about a place in memory, it doesn't really make sense to have that be negative or any sort of float, right? There's no such thing as a fractional byte. There just isn't. I mean, we can talk about one of the bits in the byte, but the way memory gets used on a computer, it's always byte by byte, full byte at a time, right? So there's no such thing as declaring 1.2 bytes or whatever, right? you'd have to declare 2 bytes and then only use some of the bits, right? Anyway, so it is strictly speaking true that all pointers are integers, but I'm going to put that aside. Okay. So what I'm doing here is the variable I'm getting is of type int pointer, meaning that it's a memory address, but it's also knows that it's pointing at an integer. So we'll come back to that later when we talk about pointer math, which we'll get to in a little bit, right? Key thing though is this is kind of a separate type of variable, an integer pointer, a pointer to an integer. And the system will know that it's an integer. So we can have a pointer to anything, right? So we could have a string pointer, if we wanted. Or a character pointer. Oh, I'm still running. So anything we want, right? And upshot is anytime you have an array, a normal array of any type, right? So you can have an array of any type. And every time you do that, what you're actually dealing with is a pointer. Because an array is just a pointer to the first element. So we'll see that more in a second. So declaring it isn't all that useful, right? So let's look at how I actually give it a value, right? So now what I can do is if I say ampersand mynum, so let's try this. I'm going to do that. And OK, so now I've declared a variable of type int pointer, and I've set its value to the address of mynum. So now what I'm going to do is I'm going to, in my output, I'm going to spit out address of mynum, right? And I'm going to spit out just my pointer, my PTR. And what we should see is they're the same thing, right? So let's try that. And we do. We get some random-ish. And again, just to be really clear with my language, when I say random, I'm not saying that you should actually use this for randomness, right? It's just don't trust it, right? Don't read anything into it, just like you want to read anything into what sandwich number you get that day, right? So we see the same thing, though, right? So ampersand mynum is the same thing as asterisk my pointer, because that's what I've set it to. So, OK. So that's another key thing about pointers. So you can declare a pointer that will just hold a memory address. If you actually print it out, no matter what type of data it's pointing to, you'll see some integer in hexadecimal. But what it's doing is it's pointing to a specific type of stuff, right? And the system will know what type of data it's pointing to. OK? Not too bad, right? So far? Just dealing with memory. Yeah, so, well, it'll, right. And it should, actually. Right now, like, what I've shown you so far is not useful. I'll just admit that, right? Where it starts to get useful is when we start looking at passing by reference, right? And it's sort of kind of an upshot for as we're going through this stuff. Later today, what we're going to do is we're going to write, like I said, a simple text adventure. And so this is the features we're going to have in the example, right? We're going to be able to go from room to room. We're going to be able to pick up inventory. We're going to be able to look at inventory. We'll be able to see what inventory is in each room. And we'll be able to transfer that from player inventory back, right? So how many global variables do you think we're going to have? Think about when we did the simple dungeon, the 2D dungeon. We had a lot of global variables, right? So somebody guess how many we're going to have? Say it? None. Exactly. We're going to have 0 global variables. So what we're going to do is we're going to declare stuff in our main, and then we're going to pass everything by reference. And we're going to have various functions that take by reference and make alterations and do whatever they need to do. And it's going to be nice and compact, and everything will just be in where it needs to be, which is a huge part of keeping yourself sane and leading to well-functioning, easy-to-maintain code. Right? Already the stuff we're doing in class is starting to kind of stretch the bounds of what I'd be comfortable just having globals for. And big projects, it's a great way to drive yourself totally nuts. But you're right that so far, I wouldn't use this either. But we'll get to more useful stuff. Okay, so what we've seen so far is we've seen how to get the address of a thing, right, by using ampersand. We've seen how to store that in a sort of special purpose box, right? A box that's not just, it knows that it's an integer, but it knows that it's a pointer to an integer, rather than just a straight integer. Like, it knows that it's a pointer to a string or a character or whatever, right? Okay, so let's say we've got an address, and we want to actually get the value of that address. Right? So for that, and this is where it starts to get weird, right? So this is the first thing we're going to see where I think this is a bad decision in the syntax of C++ that makes this whole topic more confusing than it needs to be. Because what I'm about to show you is the asterisk is going to mean something else, right? So here we've got an asterisk in a declaration. And an asterisk in a declaration means a variable of pointer type. Okay, you can almost think of it a little bit like we've seen, these keywords like unsigned, or specifically with integers, or like const, right? It's a little bit like that. It's independent of the type of value because it doesn't require that we're dealing with an integer. We can deal with any sort of thing. We could have an ogre, right, or whatever, right? But it's kind of modifying that type in a way. So it's saying instead of just having directly an integer, we have a pointer to an integer. So having an ogre itself, we have a pointer to an ogre. Right? So that's what it means in a declaration. In an expression, it's what's called the dereference operator. So let me just show you what that looks like, and we'll talk about it. Okay, so now what did I do? Right? This is why it gets confusing, right? It's doing two separate things. There should be two separate symbols. If that was the case, I think every C++ student ever would have a lot easier time with this. So let me just run this, and we'll talk about it. So check it out. So here I've got my two cout statements, right? One is ampersand mynum. So that's the address of mynum, right? And we see that it's tiny, but, it's 0019FCAC, right? So some hexadecimal address, right? But here, my next cout, I'm saying asterisk my pointer. And what we see there is 23. So the asterisk in the context of an expression is what's called the dereferencing operator. So what that does is it takes an address and it interprets what's actually there, right? So when we declared my pointer, right, asterisk meant one thing. It meant this thing that we're making is not just an int, it's a pointer to an int. Later, in an expression, notice that there's no int here, right? We're doing some operation on that thing. We're not making it, we're not creating it, we're using it. So when you create something, it's a declaration. When you use it in some way, it's an expression. So it's an expression. And that means take whatever we're talking about, take this as an address, and interpret what's there. Now, how does it know that it's an integer? Well, it knows that because we made an integer pointer. Yeah?
For the integer as for my pointer to ampersand my num. So I'm really confusing why the result is different, because the first cout is also ampersand my num.
Right. But so this is where it gets confusing, right? And again, I think that this is actually not too bad. It's just that the syntax makes it harder than it needs to be, right? So again, just this, right? What do we have? Ampersand mynum, what does that mean? Just by itself. Address of mynum, right? So this is address of mynum, right? And the way you store addresses is with a pointer. So, again, you can kind of think of variables as boxes, right? And every type of variable has a different shape, right? So, kind of think of like an int as being a square. And a float might be like a hexagon, right? So everything has its own shape, right? A pointer is kind of like, I'm trying to think of a good way to, it's kind of like, think of it as maybe a 2D version, right? So, an int is sort of like, this helps me. I don't know if it helps you guys. I hope it does. But so you can kind of think of it this way. So let's say we've got a variable that's, we can just think of an int as a cube. All right, so we've got a bunch of 3D shapes. We can have like a star shape maybe. Something, I don't know, whatever that is, right? Okay? So we can have an infinite number of different shapes, right? They're three-dimensional, right? But for each one of those, we can have a 2D shape that corresponds to it exactly, right? So we kind of think of just, the cross-section. We get, here would be a square, and here would be, something that looks kind of like that, right? So kind of like that is a visual way to put it, maybe. That think of this as the actual variable, and then we can have a pointer type for that variable. Kind of like the shadow of that object. So in any case, they're related, right? Like this is related to that, but it's kind of a different sort of thing. So in a similar sort of way, when we say int asterisk my pointer, it's not an integer exactly. It's a pointer to an integer. And that's how we store an address, right? So ampersand will give us the address of something in this context, in an expression. And I know, so if I cover this, right? If we just have this bit, int asterisk my pointer, this is a declaration. But over here, that's an expression. Just like, an int mynum equals 23, right? We talked a little bit about how there's actually two things going on there. We're declaring a variable and we're setting its value, right? So if I cover the equals 23, this is a declaration, right? Because we've seen that we can do that by itself. We can just say int mynum and not give it a value till later. I don't recommend it. It's generally a good idea to set it to some sort of default, but we can do that. That's valid C++, right? And what goes on the right side of an equal sign needs to be some sort of expression. The simplest way to think of an expression is it's a little bit of math, but it doesn't necessarily have to be math, like strict math, right? It can be other operators and other things, right? Just like looking up the address of something isn't really math, but it's an operation that gets performed on something and then we get some result, right? It's not making a new spot in memory for anything. Okay? So ampersand mynum gives us that address. What are we going to do with it, though, right? So this isn't going to fit. It's not going to fit in the cube. That's not quite the right thing for it. What it needs is a square. So that's why we say int asterisk my pointer to give us the appropriate thing to hold ampersand mynum, or the address of mynum. So, just to maybe, beat this dead horse. I don't know. Hopefully this metaphor works for you guys. But this cube might be holding something like 23, right? Whereas this square would hold something like, OX, what do we see? 0019FC, 0019FCAC, right? Yeah. Yeah, Yashim, I think you had your hand up first. Right.
So does my PTR also have its own refreshment?
Great question. Absolutely yes. So you can absolutely have a pointer to a pointer to a pointer to a pointer to a pointer. So now, realistically, there's no reason to do that. You might do that, like, there might be two levels of indirection there. But absolutely. So a pointer, what it actually is, right? And go sort of another step down, is it is an integer, right? Because it's basically, conceptually we're just counting from the first block of memory to the very last, right? And so it is an int. if we looked at, and we could totally get the address of that. So yeah, we could totally, let's just do it actually. All right, so we've got my pointer, right? So check this out. I'm going to say cout, address of and so now we get 2 memory addresses, right? So, because everything, and this is one of the fundamental things. I'm glad you asked that, because it's one of the fundamental things about pointers, right? Is you have to think about things a little bit differently. You have to kind of be thinking in terms of, this long strip of memory that we've got access to. What exactly is in each box? Where are those boxes? How many boxes are we using? All that kind of stuff. And that's, again, it makes a lot of things trickier, right, and harder to think about. But once you get through it, you become a much better engineer. So, that's kind of know that as you struggle with this stuff. Struggling with this stuff is normal, right? But at the other end of the tunnel, you end up being a much better engineer for it. Anastasia, you have a question?
I don't really know how to work that. So
Okay, that's fine. That's fine. Okay, so all right. So we've got ampersand mynum, right? Gives us the address. We create a special purpose box that is of type integer pointer, but as Yoshim's question pointed out, it is itself an integer too, right? And we can treat it like that as well. So we saw this, right? We can just output the address, but there's an inverse operation, right? So we can definitely ask ourselves or ask the system, please tell me where this given variable resides in memory, right? That's what ampersand does in an expression. In a declaration does something different. We'll get to that in a little bit. But the flip side of that is saying, given this location, what's the value there? And in an expression, well, that's what asterisk does for us in an expression. Right? So now we've seen both things that asterisk does. Right? So when we talk about pointers and making use of pointers, we're generally talking about 2 different symbols, right? Asterisk and ampersand, both of which have 2 meanings. The difference is whether it's a declaration or an expression. I know I've said that a bunch, but this is really tricky. It's tricky for bad reasons, I would say. The separation, like the logical separation, makes sense. At least I think it does. Doing something slightly different makes sense. Creating a pointer variable, right? That's one thing. And looking at a given place in memory and extracting the data, that's another type of operation, right? So, the fact that they are different things is just kind of makes sense, right? It's just unfortunate that they happen to use the same symbol. So it's easy to get confused. But, again, it's like the symbols that get used for things are kind of arbitrary, right? It's, programming, at least as we know it, came up long after the typewriter. And it was kind of like, well, we got these typewriter things, right? So we should use what's on them. And it's kind of like this random evolution of the symbols that we happen to find ourselves needing to communicate, and then repurposing them for programming, right? So, okay. So, dereferencing. Sure. Mm-hmm. Well, yeah, so they're usually represented that way, but they are integers, right? So that's a really good question, too. So an integer isn't necessarily hex, or what an integer always is binary. Like, fundamentally, it's always binary, right? But generally, on a lot of systems, they'll display memory locations as hex. So that's just kind of a convention you'll see a lot, right? And this is a good time to... I can't get through today's class without showing you this at least once. Okay, so XKCD is great. You guys, if you don't read it, you should. It's wonderful, right? So, man, I suck at this game. Can you give me a few pointers? And his friend says OX3828, et cetera, right? Gives him literally a few pointers. hardy har har, But if anything else, laugh at this as like a cheesy dad joke if you want. But at least this will hopefully, kind of lock in what a pointer is, right? It's just an integer memory address. So yeah. So actually, I want to do one more thing though on Yashin's question. So let's say we. So I'm going to say int, or let's see. Okay, so now I'm being all sorts of tricky, right? So I'm making another integer pointer. Now what? And I'm setting it to the address of my first pointer. Right? So let's try this. So I'll say, let's see, how do I want to do this? I want to. Actually, I'll come back to that. So, that's a problem. Okay. So what I've got here is a pointer. So I mean, take this with a grain of salt. I'm not recommending you guys actually do this, right? But what I want to get at is, Yashim asked, what is this thing that's a pointer, and can I have a pointer to it? You absolutely can, right? So what I've got here is I have a pointer value, right? So this is a pointer to an integer pointer. And so what's going on now is, now notice I set it to the address of my pointer, right? So if this seems confusing, it's fine, and kind of glossing over this is okay. But just for the sake of kind of completeness here, what I'm going to do is, so let's run that again. Are I still up running? I do not still up running. There we go. Okay, so I know that's hard to read, but what we see is we have three outputs, right? The first two are the same, and then the third one is different. Right? So what we've got is we've got the address of my pointer, right? And then we print pointer to pointer, right? So both of those are the same. Now if I dereference pointer to pointer, notice I get another memory address. Because what we did is we made a pointer to a pointer. Now check this out though. If I do this though, what do you think we're going to get? 23. Yeah. Good eye. Yeah, so now we get two memory addresses that are the same. We get another memory address, then we get 23. So this is definitely, not something you actually want to do. There are circumstances where it makes sense to have multiple like a pointer to a pointer, maybe. Beyond that, almost certainly not. Like, I personally can't think of situations where you'd want a pointer to a pointer to a pointer. Although you can do that. There's nothing about C++ that will prevent you from having 1,000 levels of indirection like that. Like literally 1,000. You could do that. That's fine. Fill up your memory with pointers after pointer after pointer. 2 pointers that point to other pointers. Right? It'll be turtles all the way down. And that'd be fine. It's not very useful. Yeah.
On the backup CL, how can be pointer to pointer, how can be that address?
This one?
Yeah.
Why is that an address?
Yeah.
Okay, so we're not using ampersand here, right?
Yeah.
So here it makes sense that we get an address, right? Because the very first thing we talked about today is ampersand something gives you the address of that thing, right? Now here I'm not doing that. I'm, if we didn't know what was going on up here, right? That would look surprising because this just looks like some variable name, right? But let's look at where we declared it. So what it got declared as is a pointer to a pointer to an int, and its value got set to ampersand my pointer, right? So if you just print a pointer directly, you'll get a memory address. I can also see that forget about pointer to pointer for a minute, because that's confusing and silly, honestly. But if I just print my pointer, right? So if I just do, whoops. Okay. So notice here we also get a memory address, right? Because this variable that we set up is of type integer pointer. And we filled it up with the address of some other value. Now what you want to be really careful about doing is using uninitialized pointers. So this should not work, but let's just make sure. So if this should just fail on us. It didn't. All right, so good example, right, is why to be careful. So I just did something that's a horrible idea, right? And I want you guys to look and learn from the fact that it didn't error out. It's very dangerous, right? So what I did is I declared an int pointer. That's fine. Then I did something with it without ever setting it to anything. So that's very dangerous. Because what I'm essentially doing is I'm grabbing some random piece of memory. And if I read from there, I'm not likely to get what I need. If I write to there, I could very well do very bad things. I mean, not horrible things, but crash your program kind of things, right? Writing into a random piece of memory is a very, very, very dangerous thing to do, and can very easily crash. But not all the time, right? Because you're basically rolling a big roulette wheel, and it might be the case that where you happen to write into is fine. It's just, it happens to be empty. It might also happen to be that the area of memory you write into is the code you're executing, and everything just fails. So never do that, right? It's very, very dangerous. Because what we can do is, so once we have a pointer, we can also use it to change the value that we're talking about, right? So don't worry about the pointer-to-pointer stuff for now. Maybe I'm going to comment that out. Reduce the scariness a little bit. So let's say we've got mynum. Now so we're back to just having a standard int and a pointer to it, right? So if I say my pointer equals 5, okay, what do you guys think we're gonna see? We've got mynum set to 23. We make a pointer to it. I do something to the pointer, and then I print mynum. What do you expect? 5. Yeah. So let me prove that to you. Absolutely. Yeah. So that's a really important thing to know about pointers, right? Is that they're just a reference to something, right? So if we do something to, now I want to be clear though. Notice I didn't say just my pointer, right? Here's a way to make this really bad. Here's an easy mistake to make that would be very, very bad. Now what have I done? Right, so now if I do anything with this, it's gonna set, this might error out on us actually. I would hope that this gets caught by the compiler, but let's see if it does or not. It's a very bad thing. Good, yeah. So modern compilers can often be good at catching stuff like that. So what I'm doing here is a very bad idea, and luckily the compiler's not letting us do it. Because what I'm doing is I'm setting the actual value of a pointer to some integer value. Not something you ever want to do. Ever, 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 ever. Right? You only want to, setting a pointer directly is fine, but only ever to an address. Never to an actual value. Unless that value, you know, is an address. And you know that that address is okay. Which sometimes it will be. We'll talk about that in a minute. So I'm going to fix this to be okay again. And let's talk about what's happening here. So the asterisk, right, is the dereference operator. So when it's in an expression, right? This is in an expression. So what it's doing first is it's dereferencing my pointer, And once we've dereferenced it, it's absolutely equivalent to having that actual variable. So dereferencing the pointer and then setting it to 5 is totally equivalent. I'll put this above here. 100% the same as my num equals 5. Exactly the same. It has the same effect, right? It's going about it in a slightly different way, but once we dereference that pointer, it's as if we're just dealing with that variable directly. Okay. So if we do that, we'll absolutely see that we get 5. And this is why we can pass by reference. So if we pass in an int, we get a copy, right? If we pass in anything just directly, we get a copy of that value or that data inside our function. If we pass a pointer, though, we can do stuff to it, and it'll change the actual thing, which maybe we want and maybe we don't want. Okay, so let's actually do that. Okay, well, questions so far? We're going to actually write some functions.
I still kind of don't get it why are we using pointer for like if the thing we want to like well it's just an int, not a like a modeling or something.
Yeah, so good question, and it shouldn't make sense to you yet, because what we've done so far is not useful.
Okay.
Right? What we're about to do makes it be useful, right? So again, so far, I like using ints because they're easy to talk about, right? But simple. What we're dealing with ints, which are base data types, and it's all just within our main single block of code. So it's not useful at all right now. But what we're about to do is write a function that passes by reference, and we can talk about that, and that's where it gets useful. So let's say we want a function to add two numbers. Really standard thing we've done a bunch of times, right? We might do something like this. We'll say int add to int a int b, and I'll return a plus b. I'm going to clear add some of this, let's say. Okay, so I'll cout add to 2, 3, right? So far this is, not really earth-shattering or anything, right? So we get 5 again, right? So, so we pass in two values, int a and b, and we copy them, essentially, right? So, we talked about this a little bit when we first started talking about functions, that what's really going on in this function signature is it's as if we're saying, and I'm going to write this as a comment because it's not quite right, but we're saying int a equals whatever the first argument was. And int b equals whatever the second argument was, right? So, but sort of implicit in that is two declarations, right? Because we see int a and we see int b. And that should be a really strong hint that we're actually making a new thing, right? So we're copying it. We're passing by value. So it's as if we did actually have int a and int b, new values. New chunks of memory somewhere, right? And I can prove that to you in the following way. So what I'm going to do is I'm going to give myself some values here. I'm going to say int num1 equals 2. Int num2 equals 3. And I'm going to make this num1, num2. Okay, so now what I'm going to do is I'm going to print out the addresses before and during. All right, so before we call that function, I'm going to do this. I'm going to say cout num1, and I'll use ampersand num1, so the address of num1, and then I'll give myself a space, num2, ampersand num2. And then I'll okay. So now what I'm going to do is up in my add2 function, I'm going to do the same thing. And I'll just change this because we're using A and B, so I'll say A, B. I'll change this so it's clear. Okay, so now let's try running that. So now we see that these two addresses and these two addresses are different. I know that's hard to read. Hopefully you guys are following along. But so we've got num1 and num2. So num1, for example, right, is 0018FE2C. And A is 0018FD3C. Right? So, again, specific numbers don't matter, right? But the important thing that is really key is that those are different, meaning we've got two different places in memory. And the reason we have that is because we're passing by value, meaning that we have we're making a copy, right? So okay, so that's pass by value. That's what we normally do. But a lot of times we want to pass by reference, right? So let's look at how pass by reference works, right? So what I'm going to do is let's see. Another way we could do this is, so this is a pretty standard way to add things, right? We could just return the value, right? Another way we could do it is by passing in something to fill with the value. Now, that's not necessarily the best way to go about adding, but it's really good if you want to, I'm going to go back to Carly's question from a few weeks ago about weather, right? So you've got this weather object, or something representing weather for a game, right? And you want to pass it in, as many of you guys had something like this, like a luck kind of concept for your simulation game. So you pass that into some function, right? And you want to alter it in some way inside that function, right? So let's look at how that works. So I'm going to give myself a third variable here. I'm going to say int num1, num2, right? I'm going to say int result. And I won't put it to anything just yet. And I'm not going to call this. So now I'm going to say void add by reference. Or, well, add by pointer. You'll see why I'm not saying reference in a minute. Okay, so now what I'm going to do is I'm still going to take in just int A, int B. Then I'm going to say, though, int asterisk result. Okay, so now what I've done is this function signature is a little bit different. It's taking two integers and an integer pointer. So we see the asterisk, right? But we see the asterisk in a declaration. That's the key thing. If you see an asterisk, ask yourself, is this a declaration kind of thing, or is it an expression kind of thing? If it's a declaration, it's there to say that this thing we're talking about should be of type pointer. It should be the shadow, not the 3D shape. Okay? So let's try that. So I'll say, well, there's a couple things I have to do here. So I'm going to write it wrong for a second here, just to make it hopefully a little clearer. So I'll say add by pointer num1, num2 result. Okay, so this is where things start to get confusing. It's really easy to get tripped up when you start to do this kind of stuff, right? So this is not going to work. I'll show you why. So we'll try running it. We'll get some errors. Okay, so let me get that so it stays up. All right, so this is a really, if you look at the, I don't know if you can, you should be able to see if you're sharing my screen, right? Cannot convert from int to int. if you read that really fast, that's what you're going to see. You're going to see you got an error that's claiming you can't convert from int to int. That's really weird, right? But what it's really saying is can't convert from int to int pointer. Right? So the reason I'm saying that is it's just the way humans process text. It's like you guys have ever seen these things where they'll lop out all the vowels in a word, but keep like the first letter and the last letter and maybe one or two of the things in the middle. And it's actually remarkably easy to just read the text because it's very often we're basically just scanning things more than we're really reading them, right? So when you're looking at your error, make sure you're reading it, right? Because it's actually a really good error if you're careful, right? So what it's telling us is we've got an int where what's expected is an int pointer. So that's pretty straightforward. So what's going on here is I changed it. This function is expecting an int, and an int pointer. Right? Here I've got an int, and an int. So what do I have to do to result to pass in the proper thing? Because I need to pass in its address, not just result itself. Need to add one character. Right, so I need to add the and sign, right? So this gets us almost there. So I need to say this. I need to say ampersand. So it still isn't going to work quite, because there's still one more thing I need to do. But at least now I'm passing in the right data. I'm passing in 2 ints and the address of an int. So that's going to work. Partially, right? That aspect of it's going to work. And then we'll get another problem. So we get another cannot convert from int to int pointer. So what's going on now is this is a problem, right? So that looks all innocuous, right? That looks totally blameless, right? Result equals a plus b. Well, what's result? What type is it? Int pointer, right? And what am I doing? I'm setting it to... Is this an address, though? A plus b is not an address, right? Or we better not treat it like it's an address. That's dangerous. So what I want to do is I want to dereference my address before I set its value. So this as written is bad. Because what it's doing is it's taking an address and setting it equal to some integer expression, right? I'm doing some math and setting the value of an address to that, which we should never do, with one exception, and I'll get to it in a minute. So what I want to do, though, is I just want to use the dereference operator to dereference the address. And once I've dereferenced the address, it's just like having that variable. It's no longer a pointer. It's just a normal, in this case, integer variable. So what do I have to use to dereference? Asterisk, right? So I'll put an asterisk here. And now it's going to work for us. But again, notice that we've got asterisks in 2 places doing 2 different things. Right? I think that's one of the main reasons this stuff is so confusing, personally. Right? So I've said it. I'm just going to keep belaboring it a little bit because this stuff gets confusing. Right? Asterisk here is in a declaration. We know that because there's an int. There's a key word. There's a type identifier. Right? There's a type identifier that's something that's probably a declaration. Right? And declarations can, these are basically declarations in a function signature. Same sort of thing, right? It's telling us what kind of input needs to come in. So in a declaration, it means give me of type pointer. But if it's not in a declaration, it means dereference whatever that is. And this had better be a memory address, or else that'll cause problems for us. If we try to just dereference something, it's not, because it's kind of going back to Yoshim's question, like, pointers are just integers, right? If we dereference something, if we dereference 23, we're going to just be grabbing that part of memory, and who knows what's there. They're like dragons. Dangerous. Okay, so now let's try it. And we'll get no error. But we also don't print anything. So let's, so that worked, right? It didn't do anything. So now I'm going to say cout result. Okay, so let's try that. And now we get 5, which I know, huge payoff, right? But the key thing here is that we passed by reference, or passed by pointer, rather. So this gets a little confusing. There's another thing that makes things more confusing than they need to be, in that there's this concept of pass by reference. And then there's also having an actual reference. And those are two different things, right? So I apologize. That's just the way things are, and it's unnecessarily confusing. The concept of pass by reference is what we just did. We did that concept, and that we didn't pass in the value. We didn't pass in, just a number. We passed in an address of a number. Right? So that's what passing by reference means. But in C++, there's two different ways to do it. So what we just did is we passed by pointer. Right? That's fine. There's another way to do it, though, that is a little easier to use. So we'll do that, and then we'll take a break. So this is all fine. That totally works, right? But what I'm about to show you is a little bit nicer, and I think you'll like the syntax a little bit more. It's a little bit easier to think about. It's a little less error-prone. So conceptually, I'm going to write a function that does the same thing, same idea, right? It's going to take in two integers and a reference to an integer, and it's going to fill up the third thing with the result of adding the first two things, right? So same end result. But we're going to do it in a slightly different way. I'm going to say add by reference, int a, int b, and check this out, int ampersand result. Okay, so now what's going on, right? So again, I kind of led with this, right? And now we're seeing it. Ampersand means two different things. That actually means four different things in C++, right? So we talked about how it can mean logical and bitwise and, right? I'm not talking about that today. But it can also mean two different things in the context of talking about pointers and references and et cetera, right? So if it's in an expression, it means address of. Okay? If it's in a declaration, it means give me a reference. What's a reference? Well, a reference is basically the same thing as a pointer. It's giving the same actual variable a second name. So let's look at how that works. I'll come back to this in a second. So let's say, so I'm just going to keep using my add by pointer for a minute, right? And I'm going to do this. I'm going to say int ampersand num3 equals num1. Okay. So not that you would want to do this, right? References are pretty much only used for passing stuff into functions. So what I just wrote is not something you would want to do, but I want to show it to you anyway, because it makes the idea of a reference hopefully a little clearer. Right? So what I've done here is, there's, when we say to our system, hey, computer, I want something called my num. Now what the computer's going to, or num1 in this case, right? So the computer is going to say, all right, well, I know when I see num1, what you really mean, is whatever's stored in that location, which happens to be a 2, right? And I know that every time you say num1, you really mean this piece of memory, right? So what a reference does, in this case, is it gives you another way to refer to the same piece of memory. So now what's going to happen is this is just another way of talking about num1. So right now we've got 2 and 3, right? And our code is adding 2 and 3. So I'm going to say the following. I'll say num3 equals 7. Okay? What do you think I'm going to see when I run this? Let's run it. 10. See 10. Now, the reason for that is, so we still added num1 and num2, and it's the same code, right? It's adding two numbers and storing the result and result. But what I did here is, when I used the ampersand here, in a declaration, it's different than when you used it in an expression. It's saying, give me a reference to that thing, which is a very similar concept to the pointer. It's another handle, right? But the nice thing about it is we don't have to worry about dereferencing, right? So if I say num3 equals 7, I can use num3 just like a normal int. It is an integer. It just happens to be the same integer. Not the same value as num1, it's exactly the same. It occupies the same place in memory. Changing one absolutely changes the other, because they're not separate. We have, it's kind of like we have this box named num1, right? So it's kind of like, it started off with 2, right? So num1, points at this box filled with 2, right? By creating a reference, what I'm doing is I'm saying, hey, there's another way to point at that thing, and it's going to be called num3, which points at the same thing. Yeah?
How we can distinguish the ampersand? Sometimes they call or sometimes.
Right. So the key thing, ampersand and asterisk, right, is it in a declaration or an expression? So a declaration is something like this, right? Int num1. Right? You should see a type along with it. So it's basically two things. When you're creating a variable or in a function definition. Both of those cases are declarations. So this is a declaration. Sorry. So this is a declaration. So is this. So when we see the ampersand here, it has the same function, because it's a declaration, as it does here. When it's in an expression, meaning that there isn't a type, then it's doing something different. It means address of, right? So, up here, right? Now, it is true that this half is a declaration, right? But on the other side of the equal sign, that's an expression. Because we could write this separately, right? We could say this. We could say, that's totally fine too, right? And that makes it a little clearer that this is one operation, and this is another operation. So this is a declaration, meaning that asterisk has one meaning, meaning give me a pointer of that type, right? And if we use it, and here, right, asterisk means dereference. So take that address and look at what's stored there. Same thing with ampersand. Two different things. And honestly, like I said, I think it's just unnecessarily confusing to reuse those symbols, but that's what we've got. So, sorry. If it feels confusing, it's because it is confusing. It's okay. So that's what a reference is, right? So references used like this, honestly, there's no reason to ever use them. Well, I won't say never, right? There's not much reason to use them like that. But the nice thing about references is you can use them to pass stuff into functions, and then you don't have to worry about all this dereferencing stuff, right? So, okay. So let's go back up here. So I've got add by reference, right? So I'm taking in two just normal integers, and then I'm taking in a reference to an integer. So, it's in normal function arguments, right? It's like we say int a equals whatever the first thing was. But here's the new concept as of today, by value, right? So we're saying make a copy. So what we're really saying is int a equals a copy of whatever the first thing was. Is kind of more accurate, right? We're doing the same thing for b. But in this case, we're saying int result. I'm going to, because I'm about to write some just normal English. So a reference. So upshot of that is we can make changes to it. So once we've got a reference, right, we can treat it just like a normal variable. In this case, an int, or whatever else we've got, right? It's just a normal variable, but it refers to the same thing. So if we make changes to our reference, it's going to change whatever the original was. So, so here, what I'm going to do is I'm going to say result equals A plus B, right? And notice I'm not using an asterisk here. Because in this case, this result, right, is a reference to whatever we passed in, so we can treat it just like a normal integer variable. It's totally fine. But it has the upshot of it will actually alter the thing that got passed in, so we can make changes, and that'll work. So I'm going to comment this out, and I'll say add by reference num1, num2. And notice I also don't have to have an ampersand when I call this, right? So what's going to happen here is these two will be passed by value. This will be passed by reference. So it makes the calling and the utilization is a little nicer, right? But it gives us the same benefits that we're passing stuff by reference, not by value. So let's see. So we should still get 10 because I've got that going on. But I'll comment that out for now. Let's just comment that out. So we'll be back at 5. So run that. And we get 5 once again. Because we passed in something to fill up, kind of, which is actually a pretty standard practice. It's really common to do that, to kind of like pass in a reference to something that you want either altered or filled in some way. That's a totally common thing to do. Yeah.
On the not that this side, I mean offside.
Yeah, sure. I mean, I'll scroll up a little bit. Oh yeah, it's so yeah.
I mean, and yeah, on this part, the green one.
Mm-hmm.
Why you put? I mean, why you attach to the n% digit? Because integer and space digit.
Right. So, oh yeah. So good. Yeah, there's another thing that makes this more complicated than it needs to be, is that you can actually, so both with the asterisk and the ampersand, the spaces, you can, actually they kind of work either way. So you can have it like that, or you can have it like this, or you can have it like that.
So it doesn't matter.
Doesn't matter in that case. Let's just do that. Let's everybody do that. Pick one and stick with it. But just know that you'll see it differently sometimes, right? And that's just part of the joy for this C++. Yeah. But the key thing is just like we could, right? So again, I don't. It's not like I expect you guys to ever really do this, but you can, make a reference to a variable, right? So int ampersand num3 equals num1, right? This is not getting the address. I'm not using the address directly. I'm just saying, give me another way to refer to the same block of memory. And if I do that, it's exactly the same thing. There's only one integer involved, in num1 and num3 in this case. So this isn't something you want to do, but that's kind of what's happening when we pass something in by reference. We get a reference to the thing. So we can do whatever we want to it, including changing its makeup or adding stuff to it, whatever we want to do, right? Yeah. One last thing on that, and then we'll take a break. I promise this will be quick. So this is really, really good, very, very useful, right? Passing stuff in is great. This is how you start breaking up your code in good ways. But there is a danger here in that sometimes what you pass around, right? So in this case, what we passed around was a result. We're asking our program to fill up that result with a value. Totally cool. Other times, though, what we'll want to do is we'll want to pass something in, but we want to be sure that it won't change. So it might be the case that, I'm going to go back to the sim example that you guys all worked on. So let's say you did have some sort of complex structure for luck, right? And you want to pass it in to everything, right? Because luck's going to kind of play a role in everything. but you don't want it to change. You don't want it to be the case that you harvest your grain, and it might be the case that you're lucky or you're not, but the action of harvesting shouldn't alter your luck. I mean, maybe it does, but let's just say that that's not the game we're making. We're going to set luck like once per month, let's say, right? And whatever a month is in game time. Might be once a turn or whatever, right? And we want luck to be consistent for that, right? So what you'll sometimes see is this. So let's just say we have a luck number, right? And just to keep things short and simple, I'm going to just make it an int, right? So I'm going to say int luck equals 10, let's say, right? And let's say I, harvest grain. Okay, so I'm going to find out how much I harvested. And I want luck to be involved, but I don't want luck to have any way to change in the course of harvesting, right? So what I'll do is this. Also, I'm going to return an int, right? Harvest grain. And I'm going to say int luck. Okay, so now I can return. Let's just return 5 for now, right? So what the danger here is that, and again, let's just say for the sake of the design of this imaginary game, I don't want luck to ever change in this when I'm harvesting grain. I could be doing a lot of math here and utilizing luck, and I could accidentally make luck change, right? So a good idea in that context is to do the following. Const int ampersand luck. So what's going to go on there is, so far, if we ignore const, right? Luck, we can just treat it like a normal variable, right? I can just say, return luck even. I could just do that, right? That's totally fine. And just for the sake of, actually having stuff we run, let's do this. I'll, say something like, yeah. Okay, so we should see harvested 10. That's all fine, right? So that's totally cool. But if I make a const, now it prevents me from being able to change it. So let's see what happens if I say luck plus equals 1 or something, right? So if I do that, if this wasn't const, it'd be fine. But if I do that now, we get an error. So you see, luck you cannot assign to a variable that is const. So sometimes errors are actually really good. So setting yourself up to get errors is actually sometimes as important as being able to fix them. Because getting that pointed out to you is actually really good. Because this is one type of way that really subtle and hard to fix problems can come about. If you're accidentally changing something that wasn't supposed to change. And, in this case, it's very obvious that I'm changing it. But, you write up, there might be 100 lines of code here to do harvesting, right? And luck might be involved in more than one of those. And I might accidentally be changing it. So if you know that this shouldn't change, add const. Okay. Questions? You guys know pointers now. Awesome.